In 100 billion years, the night sky will be absolutely black. Not a single star, not a single galaxy visible anywhere you look. Just endless, impenetrable darkness stretching in all directions. And our distant descendants, if they even exist at that point, won't be able to figure out that the universe was once filled with light, filled with possibilities, filled with other worlds beyond counting. They'll think the Milky Way is the entire universe, everything that exists. And they'll never know that we, their ancestors, could see trillions of galaxies stretching away in every direction. Galaxies we could observe but never, ever reach. This isn't science fiction. This isn't some pessimist's gloomy prediction. This is mathematical inevitability, written into the very fabric of space-time itself. And today, you're going to learn why humanity is forever locked in its cosmic prison, why all our dreams of intergalactic travel are doomed to remain dreams, and why the very structure of the universe makes us eternal prisoners of a tiny island in an infinite ocean of void. 3 great barriers stand between us and the stars of other galaxies. The first is the fabric of space itself, which stretches faster than light, carrying away everything we might want to reach. The second is the monstrous distances that turn even a beam of light into an infinitely slow traveler. The third is time, which we simply don't have, because the universe has already begun closing the doors, and with each passing second, more galaxies disappear beyond the event horizon from which there is no return. Today you're going to learn something that will change how you perceive the cosmos forever. Something that astronomers and physicists understand but rarely speak aloud to ordinary people. You'll understand why we're not just alone, we're isolated, trapped, condemned to eternal confinement within a single galaxy while trillions of other worlds slowly sink into impenetrable abyss. Let's start with what they always told us, with that beautiful picture painted by popular science films and optimistic futurists. They tell us that space is an infinite frontier waiting to be explored, that technology develops exponentially, and sooner or later we'll build ships capable of reaching other stars, other galaxies, other universes even. They show us warp drives from science fiction, wormholes connecting distant points in space, and promise that the laws of physics are just temporary limitations that human genius will inevitably overcome. They tell us that Andromeda, our nearest large galactic neighbor, is only 2.5 million light-years away. And this distance is presented as a challenge, as a goal, as something fundamentally achievable with sufficient technological development. Like once upon a time, oceans seemed insurmountable, and then people learned to build ships. Once upon a time, the sky was inaccessible, and then airplanes appeared. So why not imagine that one day we'll fly to Andromeda? This picture is beautiful. It inspires. It makes you dream of a future full of adventures among the stars. But it's built on a fundamental misunderstanding of how our universe works. Or, what's even worse, on a conscious silencing of an inconvenient truth. Because the reality is quite different, and it's much more frightening. Let's start with a simple fact that's rarely mentioned in popular space stories. The universe is expanding. Everyone knows this, but few understand what this actually means. When we say the universe is expanding, we don't mean that galaxies are flying apart in some empty space like fragments of an explosion. No, space itself is stretching. Imagine the surface of a balloon with dots drawn on it. When you inflate the balloon, the dots don't move across the surface, they stay in place. But the distance between them increases because the surface itself becomes larger. The same thing happens with the universe. Galaxies aren't flying through space away from each other. Space between them is literally being created, appearing out of nowhere, stretching the distance. And the speed of this stretching depends on scale. The greater the distance between two objects, the faster the space between them stretches. And here's where the nightmare begins. At a certain distance from us, the speed of space expansion exceeds the speed of light. This doesn't violate any laws of physics because nothing is moving through space faster than light. Space itself is stretching. This is called the Hubble horizon, and it's located approximately 14 billion light-years from us. Everything beyond this boundary is receding from us at superluminal speeds. Not because it's moving that fast, but because the space between us and these objects is stretching faster than light can cross it. And this is only the beginning of the problem, because the expansion of the universe is accelerating. Every second, every minute, every day, space stretches faster and faster. The culprit is dark energy, a mysterious force comprising almost 70% of all energy in the universe. We don't know what it is. We don't understand its nature, but we know exactly what it does. It pushes the universe into expansion at a constantly increasing rate. This means the horizon isn't standing still, it's shrinking. The region of the universe accessible to us, even theoretically, is becoming smaller with each moment. Galaxies that are on the edge of reachability today will be beyond the horizon tomorrow. And when they cross that invisible boundary, they'll disappear forever. Not in the sense that they'll cease to exist. They'll continue living their lives with billions of stars and possibly with intelligent beings looking at their own sky. But for us, they'll cease to exist. Their light will never reach our eyes. No signal, no ship. Nothing will be able to overcome the distance that's growing faster than the speed of light. And here's the scariest part. We're already too late. Most of the galaxies we see in the night sky are already unreachable. The light we receive from them today left billions of years ago when they were closer. Since then, they've moved so far away that no signal sent by us right now will ever catch up to them. We're seeing ghosts. We're observing galaxies we can never contact again, let alone reach. Out of approximately 2 trillion galaxies in the observable universe, the overwhelming majority are already lost to us forever. They're beyond the cosmological event horizon, an invisible boundary that nothing can cross in our direction. These galaxies continue to exist, but they exist in a region of space-time that is as inaccessible to us as a parallel universe. And the situation only gets worse. Each year, more galaxies cross this boundary. In a few tens of billions of years, practically all galaxies will disappear beyond the horizon, and in 100 billion years, not even a trace of them will remain. Their light, which is still traveling to us now, will stretch to such an extent that it becomes indistinguishable from cosmic microwave background radiation. They'll literally dissolve into darkness. But wait, you'll say, what about Andromeda? It's approaching us, not receding. This is true. Andromeda is one of the few large galaxies gravitationally bound to the Milky Way. In approximately 4.5 billion years, our galaxies will collide and merge into one giant elliptical galaxy already nicknamed Milkomeda. Does this mean we can reach Andromeda's stars? Technically, yes, Andromeda is reachable. But this is just an illusion of hope, because Andromeda is an exception, the rarest exception. It and several dozen dwarf galaxies in our local group are the only galaxies we'll ever be able to visit, even theoretically. Everything else, 2 trillion galaxies, an infinite number of stars, possible planets, possible civilizations, is forever cut off from us. Imagine this, a universe full of life, full of wonders, full of worlds we'll never see up close. Civilizations that may exist right now, looking at the same laws of physics, dreaming of the same stars, and being forever separated from us by a barrier of expanding space. We'll never learn of their existence. They'll never learn of ours. 2 intelligent species can exist in one universe, dream of contact, strive for the stars, and be doomed to eternal loneliness, simply because the space between them grows faster than they can cross it. This isn't a technical problem that can be solved with more advanced technologies. This isn't an engineering challenge waiting for its genius. This is a fundamental law of nature written into the very structure of reality. The universe is designed to isolate all life in small islands scattered across an infinite ocean of void. And these islands drift farther and farther from each other until the distance between them becomes infinite. The official picture they paint for us, the picture of an infinite cosmic frontier awaiting conquest, crumbles when confronted with reality. We're not explorers on the threshold of a boundless ocean of possibilities. We're prisoners whose cell is infinitely expanding, but whose walls remain impenetrable. But there's something else, something even more disturbing. Because the expansion of the universe is only the first barrier, only the tip of the iceberg, only the first layer of the cosmic prison in which we find ourselves. The reality is much darker, much more hopeless, much more beautiful in its ruthless honesty. Let's talk about the second barrier, about space and time themselves, which turn even the distances accessible to us into insurmountable chasms. About the speed of light, which transforms from nature's greatest achievement into a prison wall. About why even flight to the nearest star, let alone the nearest galaxy, may prove impossible for any technological civilization. Because the problem isn't only that the universe is expanding, the problem is that it's unimaginably enormous. And this enormity makes interstellar travel practically impossible, and intergalactic travel absolutely impossible. But before we plunge into this abyss of despair, let me remind you how small you are, how small we all are, how insignificant our planet, our solar system, our galaxy is. Tiny specks of dust on the scales of the universe. Earth has a diameter of about 12,700 kilometers. This is our home, the only world we truly know. But Earth is a grain of sand compared to the Sun, whose diameter exceeds 1,400,000 kilometers. More than 1 million Earths could fit inside the Sun. And the Sun is an ordinary star, not even particularly large. There are stars that would contain hundreds of suns. There are stars whose diameter exceeds Jupiter's orbit. But let's stay within the scale of our solar system for now. From Earth to the Sun is about 150 million kilometers. This unit is called an astronomical unit. Light crosses this distance in 8 minutes and 20 seconds. When you look at the Sun, you see it as it was 8 minutes ago. To Neptune, the farthest planet in our system, light travels about 4 hours. To the boundary of the heliosphere, the region where solar wind meets interstellar space, about 17 hours. To the hypothetical Oort cloud, from where long-period comets come, up to a year. And this is just our solar system, a tiny bubble around one ordinary star on the outskirts of one ordinary galaxy. The nearest star to us, Proxima Centauri, is located at a distance of just over 4 light years. This means that light, the fastest phenomenon in the universe, flies to it for more than 4 years. 4 years of continuous travel at a speed of nearly 300,000 kilometers per second. For comparison, the fastest spacecraft created by humans, the Parker Solar Probe, reaches speeds of about 200 kilometers per second at the closest approach to the Sun. At this speed, a journey to Proxima Centauri would take more than 6,000 years. Voyager 1, the most distant artificial object from Earth, has been flying for more than 46 years. During this time, it has covered a distance of less than 1 light day. It would take more than 70,000 years to reach Proxima Centauri. And this is the nearest star, one of approximately 200 billion stars in our galaxy. Now imagine a galaxy. The Milky Way has a diameter of about 100,000 light years. To cross it from edge to edge at the speed of light would take 100,000 years. 100,000 years is more than the entire history of human civilization, more than the time Homo sapiens has existed as a species. And this is just one galaxy. And Andromeda, our nearest large galactic neighbor, is 2.5 million light-years away. 2.5 million years of flight at the speed of light. This is enough time for a species to go through a complete evolutionary cycle, for entire civilizations to arise, flourish, and perish, for continents to shift hundreds of kilometers, for Earth's climate to change beyond recognition dozens of times. And Andromeda is the nearest large galaxy, the one we can theoretically reach, the one gravitationally bound to us. But reality is even more cruel. The speed of light is 300,000 kilometers per second. This number sounds incredibly fast, and it really is incredibly fast by any human standards. In 1 second, a beam of light can circle the Earth almost 8 times. In a second, it covers a distance that would take an airplane more than a year to fly. This is a speed impossible to imagine, impossible to feel, impossible to experience. And yet this is the most rigid limitation in the entire universe, an absolute limit. A wall that cannot be broken through with any technology, any energy, any genius. This isn't just an engineering limitation like the sound barrier, which once seemed insurmountable and then was overcome. This is a fundamental property of space-time itself. The speed of light isn't just the speed at which light travels, it's the speed of causality. It's the maximum speed at which any information, any influence, any interaction can propagate in the universe. Albert Einstein discovered this more than 100 years ago, and since then every experiment, every observation, every measurement has confirmed his correctness. Special relativity isn't a hypothesis, isn't an assumption, isn't one of the possible models. It's a tested, proven, irrefutable law of nature. And this law tells us something very unpleasant. Nothing possessing mass can reach the speed of light. Never, under any circumstances. The reason lies in the very nature of mass and energy. When an object accelerates, its kinetic energy increases. This is intuitively understandable, but at speeds approaching the speed of light, something strange happens. The energy required for further acceleration begins to grow not linearly, but exponentially. With each additional kilometer per second, more and more energy is required. And as you approach the speed of light, this curve rushes to infinity. To accelerate an object with mass to the speed of light would require infinite energy. Not very large, not astronomically huge. Infinite. All the energy of the universe multiplied by infinity wouldn't be enough to accelerate a single electron. This is mathematics, and mathematics is relentless. Let's look at specific numbers. A spacecraft with a mass of 1,000 tons, approximately the mass of the International Space Station, when accelerating to 1% of the speed of light, will require energy equivalent to approximately 100 megatons of TNT. This is more than the most powerful thermonuclear bomb ever detonated by humanity. And this is only 1% of the speed of light. At 10% of the speed of light, the energy increases approximately 100 times. This is already the equivalent of tens of thousands of thermonuclear warheads, energy capable of destroying a civilization. At 50% of the speed of light, relativistic effects become significant. The ship's mass, or rather its inertia, increases by approximately 15%. The energy required for acceleration rises to magnitudes comparable to the annual energy consumption of the entire planet Earth. At 90% of the speed of light, the ship's inertia increases more than twice. Acceleration energy is measured in magnitudes equivalent to small asteroids completely converted into energy, according to Einstein's formula. At 99% of the speed of light, inertia increases 7-fold. Energy tens of times greater than at 90%. At 99.9%, inertia increases 22 times. At 99.99%, 70 times. And so on, to infinity. The closer to the speed of light, the more energy required for each additional meter per second, And on the last, infinitely small segment to the speed of light, infinitely large energy will be required. This means that even if humanity somehow mastered the energy of stars, even if we learned to use all the energy of the galaxy, we could never reach the speed of light. We could approach it theoretically. With sufficient resources, we could reach 99% or even 99.9%. But that last tiny gap will remain insurmountable forever. And even if we could travel at a speed very close to light, the distance problem wouldn't go anywhere. To Andromeda, it would still be 2.5 million years of travel, even at an impossible 99.99% of the speed of light. But here, another relativistic effect comes into play, which many consider a loophole: salvation, hope, time dilation. According to special relativity, time for a moving object flows slower than for a stationary observer. The faster the motion, the stronger the dilation. At a speed close to light, time aboard the ship can practically stop relative to the external universe. This means that for the crew of a ship flying to Andromeda at 99.9% of light speed, the journey won't take 2.5 million years, but much less. At this speed, the time dilation coefficient is approximately 22, meaning for the crew, about 113,000 years will pass. This is still unimaginably long. But wait, the optimist will say, what if we fly even faster? At 99.99% of the speed of light, the dilation coefficient rises to 70. The journey would be reduced to approximately 35,000 subjective years. Add another 9, and the coefficient grows to 220. The journey will take about 11,000 years for the crew. Theoretically, at a sufficiently extreme speed, you could reduce the subjective travel time to human scales. At a speed differing from light by a fraction of a percent, the crew could reach Andromeda in a few decades of subjective time. Sounds encouraging. Don't be too quick to rejoice. First, energy. To reach such speeds would require energy exceeding everything humanity is capable of even imagining. We're talking about complete conversion of mass into energy, with efficiency exceeding thermonuclear fusion by thousands of times. We're talking about antimatter in quantities that would require processing entire planets. We're talking about technologies that are not just beyond the horizon of our understanding, but beyond the horizon of the horizon. Second, braking. Accelerating to near light speed is only half the problem. You also need to brake at the destination. And braking requires as much energy as acceleration. So all the astronomical figures need to be multiplied by 2. Third, fuel. Any ship must carry its fuel with it, and fuel has mass, and this mass also needs to be accelerated. This creates a vicious circle. The more fuel needed for acceleration, the greater the ship's mass, the more fuel needed to accelerate this mass. Mathematics shows that to achieve a significant fraction of the speed of light on chemical fuel would require a rocket whose fuel mass exceeded the mass of the observable universe. Even with nuclear or thermonuclear fuel, the numbers remain absurd. Even with antimatter, the most energy-dense fuel known in physics, an intergalactic ship would require reserves measured in millions of tons of antimatter. For comparison, throughout human history we've produced less than 1 nanogram of antimatter, a billionth of a gram. But suppose, by some miracle, we solved the energy and fuel problem. Suppose we built a ship capable of accelerating to 99.99% of the speed of light. Suppose the crew is ready to spend several decades of subjective time on the journey, understanding that millions of years will pass on Earth. There remains one more problem, and it's perhaps the most insurmountable of all. Interstellar space isn't empty. It seems empty by human standards, on average about 1 hydrogen atom per cubic centimeter. This is a vacuum deeper than any vacuum we can create in the laboratory. But at near light speeds, even this almost non-existent gas turns into a deadly weapon. Imagine a ship flying at 99% of light speed. That's approximately 297,000 kilometers per second. Each hydrogen atom encountered on the path crashes into the hull with relativistic energy. And this energy is enormous. At such speeds, the kinetic energy of one proton is comparable to the energy of a macroscopic bullet. One tiny hydrogen atom carries the energy of a pistol shot, and there are billions and billions of such atoms on the path. This is called relativistic bombardment. Interstellar gas, usually invisible and harmless, turns into a stream of deadly radiation. Protons and hydrogen atoms crashing into the ship's hull generate cascades of secondary particles, including hard gamma radiation. The crew would receive a lethal dose of radiation in a matter of seconds. But that's not all. In interstellar space, there aren't just gas atoms, there are dust particles. Tiny particles the size of microns. At ordinary speeds, they're harmless. At near light speeds, they become projectiles with the energy of thermonuclear warheads. A collision with a dust particle the size of a milligram at 99% of light speed would release energy equivalent to several kilotons of TNT. This is enough to vaporize any ship, and these particles are impossible to detect in advance, impossible to evade, impossible to defend against. You could build a shield, but the shield must be massive enough to withstand impacts, and this adds mass that needs to be accelerated, which requires more energy and fuel. The vicious circle closes. But perhaps there's a way around all these limitations. Science fiction offers many ideas: warp drives bending space, wormholes connecting distant points in the universe, hyperspace, parallel dimensions. Could any of this work? Let's start with the warp drive. The concept was proposed by Mexican physicist Miguel Alcubierre in 1994. The idea is not to move the ship through space, but to move space itself along with the ship. Create a bubble of curved space-time that contracts in front of the ship and expands behind it. The ship inside the bubble remains stationary, but the bubble moves at superluminal speed. Mathematically, this solution works. Einstein's equations allow the existence of such a configuration of space-time, but there are several problems. First, creating such a bubble requires exotic matter with negative energy density. This isn't antimatter. Antimatter has positive energy like ordinary matter. This is something completely different, something that possibly doesn't exist in the universe at all. We've never observed exotic matter. We don't know if it can be created. We're not even sure that the laws of physics allow its existence in macroscopic quantities. Second problem. Even if exotic matter exists, a monstrous amount of it would be required. Alcubierre's original calculations showed that creating a warp bubble would need mass energy exceeding the mass of the entire observable universe. Later physicists refined the calculations and reduced this figure to Jupiter's mass. But even Jupiter's mass is 318 times Earth's mass. And this mass somehow needs to be converted into exotic matter, which, I remind you, possibly doesn't exist at all. Third problem. Even if a warp bubble can be created, it's unclear how to control it. Inside the bubble, the ship is isolated from the external universe. No signals can exit or enter. The crew won't be able to see where they're flying, won't be able to correct course, won't be able to brake upon arrival. Fourth problem. Some calculations show that when exiting warp mode, energy accumulated on the front surface of the bubble would be released in the form of catastrophic gamma radiation that would destroy everything in its path. Arrival at the destination would mean sterilization of an entire star system. The warp drive remains a mathematical toy with no practical application. It requires physics that's possibly impossible, energy that's impossible to obtain, and creates problems impossible to solve. Wormholes are another popular idea. Theoretically, general relativity allows the existence of tunnels through space-time connecting distant points. Instead of flying 2.5 million light-years to Andromeda through ordinary space, you could walk through a short tunnel. The problem is that no one has ever observed a wormhole. No one knows if they exist in nature. And even if they do exist, they're apparently microscopically small, the size of the Planck length, that is, trillions upon trillions of times smaller than an atom. To use a wormhole for travel, you'd somehow need to expand it to macroscopic sizes, and for this, again, exotic matter with negative energy is required, the same kind that possibly doesn't exist. Moreover, calculations show that even if you managed to create a traversable wormhole, it would be extremely unstable. Any perturbation, including an attempt to pass through it, would cause collapse. The wormhole would collapse before anything could pass through. And even if by some miracle you manage to create a stable, traversable wormhole, the question remains, how do you open it where you want to go? To connect Earth with Andromeda, you'd somehow need to deliver one end of the wormhole to Andromeda, and for this, you'd first need to reach Andromeda the ordinary way. Vicious circle.
Hyperspace, subspace, parallel dimensions.
All of this remains pure science fiction without any theoretical foundation.
There's no evidence that such concepts relate to reality. They don't follow from known laws of physics. They're not observed in any experiments. They exist only in the imagination of fiction writers. What remains? Remains to acknowledge the bitter truth. Physics, as far as we understand it, offers no way to overcome cosmic distances in reasonable time. The speed of light is an absolute barrier. Energy requirements for approaching this barrier are astronomical. The dangers of interstellar space are deadly, and all proposed workarounds require physics that's possibly impossible. This doesn't mean physicists have stopped searching. Every year, new papers appear proposing new ideas. Quantum teleportation, though it doesn't allow transmitting information faster than light. Manipulations with space-time at Planck scales. Use of additional dimensions predicted by string theory. But all these ideas remain speculations, theoretical exercises without experimental confirmation. And even if one of them proves correct, practical implementation would require technologies beyond any reasonable forecast. Science is honest, and honesty requires acknowledgement. We don't know a way to travel between galaxies. We're not even sure such a way exists. All known laws of physics tell us that intergalactic travel is impossible.
And while there's always a chance that we're missing something, that there's some unknown physics that will open doors to the stars, counting on this would be not scientific optimism, but blind faith. We're trapped. Not temporarily, not until technology develops sufficiently. We're fundamentally trapped by laws of nature we didn't choose and cannot change. And this brings us to the next question. If we can't reach other galaxies, what does this mean for our future? What happens when the only island accessible to us, our local group of galaxies, remains alone in the universe? When all other galaxies disappear beyond the horizon, taking with them trillions of stars and possibly trillions of civilizations. This is a story about how the universe slowly goes dark, how light yields to darkness, how isolation becomes absolute. But before we move to this grim prospect, let's look at specific examples. Let's look at real cosmic objects, real distances, real barriers. Because only through specifics can you truly understand the scale of our prison. Take a specific example, the galaxy named GNZ11. This is the most distant galaxy humanity has ever observed. It's located at a distance of approximately 13.5 billion light-years from Earth. The light we receive from it today was emitted just 400 million years after the Big Bang. We see this galaxy as it was when the universe was still an infant.
But here's what's interesting.
Although light traveled to us for 13.5 billion years, the galaxy itself is now much farther away. Remember space expansion? While light traveled to us, space between us and GNZ11 continued stretching. Today, this galaxy is approximately 32 billion light years away from us, and it's receding at a speed exceeding the speed of light. This means GNZ11 is already lost to us forever. Even if we sent a signal in its direction right now, that signal would never reach it. Space between us grows faster than light can cross it. We're seeing a ghost of a galaxy that no longer exists for us in reachable reality. And GNZ11 isn't an exception. It's the rule. The overwhelming majority of galaxies in the observable universe are already beyond the horizon of reachability. We see their light emitted billions of years ago, but they themselves have long gone beyond our cosmic horizon. Let's look at scales closer. The universe is organized into a hierarchical structure. Stars unite into galaxies, galaxies into groups, groups into clusters, clusters into superclusters, and even superclusters form still more grandiose structures, filaments and walls separated by giant voids. Our Milky Way is part of the local group, a cluster of approximately 50 galaxies gravitationally bound to each other. The local group occupies a region of space with a diameter of about 10 million light years. This is a lot by human standards, but negligibly small by cosmic ones. The local group, in turn, is part of the Virgo supercluster, a giant structure containing about 2,000 galaxies. The Virgo supercluster's diameter is approximately 110 million light years. But even this isn't the limit. The Virgo supercluster is just part of an even more massive structure called Laniakea. This is a supercluster of superclusters containing about 100,000 galaxies and extending 500 million light years. And even Laniakea is a speck on the scale of the observable universe, which extends 93 billion light years in diameter and contains about 2 trillion galaxies. 2 trillion. That's 2 with 12 zeros. If each galaxy were a grain of sand, all the galaxies in the universe would fill several Olympic swimming pools. And of all this unimaginable wealth, we can hope to reach only a tiny handful, several dozen galaxies of the local group. Let's look at these galaxies accessible to us more closely. Andromeda is the largest galaxy in the local group. It contains about 1 trillion stars, approximately 5 times more than the Milky Way. Its diameter is about 220,000 light years. It's approaching us at a speed of approximately 110 kilometers per second. In 4.5 billion years, Andromeda will collide with the Milky Way. This will be a grandiose event, stretched over hundreds of millions of years. The galaxies will pass through each other. Their gravitational fields will distort the shape of both, tear stars from their orbits, create giant tidal tails of gas and dust. Then they'll diverge, slow down, return to each other, and collide again. And so several times until they finally merge into one giant elliptical galaxy. But galactic collision isn't collision in the usual sense of the word. The distance between stars is so enormous that the probability of physical collision of 2 stars is practically zero. Galaxies will pass through each other like 2 swarms of bees, almost not noticing each other's presence at the level of individual stars. However, gravitational disturbances will be colossal. Star orbits will change chaotically. Some stars will be ejected into intergalactic space at enormous speeds. These are so-called hypervelocity stars, accelerated by gravitational slingshots to 1,000 kilometers per second or more. Other stars will fall to the galactic centers, where supermassive black holes await them. Our Sun will most likely survive this merger. By that time, it will be in a late stage of its evolution,
a red giant that has swallowed Mercury, Venus, and possibly Earth. But even if the solar system somehow survives, its position in the new galaxy will be completely different. Maybe we'll be closer to the center, maybe farther. Maybe we'll be ejected into the halo, the outer, rarefied region of the galaxy. Triangulum, or the Triangle Galaxy, is the third largest galaxy in the local group. It's approximately 5 times smaller than the Milky Way and contains about 40 billion stars. Distance to it is about 3 million light-years.
It may also participate in the future merger, though its fate is less certain. Besides these giants, the local group contains dozens of dwarf galaxies. The large and small Magellanic Clouds, satellites of the Milky Way visible to the naked eye from the southern hemisphere. Dwarf galaxies in Sagittarius, Draco, Ursa Minor. Many of them are so dim they were discovered only in recent decades. All these galaxies are gravitationally bound. They orbit around a common center of mass, influence each other, sometimes collide and merge. And all of them are our only hope for an intergalactic presence. The only worlds beyond the Milky Way that we'll ever be able to visit. Even if humanity survives the next billions of years, even if we master interstellar travel, even if we colonize the entire galaxy, we won't go beyond the local group. But even within this limited region, challenges remain colossal. The distance to Andromeda is 2.5 million light-years. This is 625,000 times more than to Proxima Centauri. If a journey to the nearest star with current technologies would take 70,000 years, a journey to Andromeda would take more than 40 billion years. This is 3 times longer than the current age of the universe. Of course, with more advanced technologies, this time can be reduced, but even at near light speeds, even accounting for relativistic time dilation, we're talking about journeys lasting millennia or tens of thousands of years of subjective time, about ships that must function without breakdowns for millions of years by external observer clocks, about life support technologies exceeding everything we can imagine. And this is assuming the travelers even want to fly, because for them, thousands of years will pass. But for those remaining on Earth, or whatever planet humanity lives on then, millions of years will pass. By the time they arrive, the civilization that sent them will have long disappeared. Their language will be dead, their culture forgotten. They'll arrive in a completely alien world, having nothing in common with the one they left. Intergalactic travel isn't just a technical challenge, it's existential. It's a one-way journey, not only in space, but in time. A journey with no return, not only to the place of departure, but to the era of departure. But suppose some future civilization decides on this. Suppose there are daredevils ready to leave everything they know for the stars of another galaxy. What challenges will they face? The first challenge is the intergalactic medium itself. Space between galaxies is even emptier than interstellar. Matter density there is thousands of times lower. This might seem like an advantage. Fewer particles means less relativistic bombardment. But there's a flip side. In intergalactic space, there's nothing. Literally nothing. No stars you could use for gravitational maneuvers, no planets for refueling or repairs, no resources of any kind. If something goes wrong halfway to Andromeda, and at distances of millions of light years, something will definitely go wrong. There's nowhere to expect help from. The ship must be completely autonomous, capable of handling any problem independently. Second challenge is navigation. At such distances, even tiny course errors lead to colossal deviations. An error of 1/1,000,000th of a degree at launch means missing by thousands of light years upon arrival. The ship must constantly correct course with unimaginable precision over millions of years. Third challenge is time. Any equipment degrades, any mechanisms break, any computers fail. Over millions of years, even the most reliable systems will fail many times over.
The ship must be capable of complete self-reprocessing, creating spare parts, repairs, and upgrades without any external help. Fourth challenge is biology. If there are living beings aboard, how do you maintain their life over thousands of years of subjective time? Cryogenic freezing remains science fiction. We don't know a way to freeze and thaw complex organisms without fatal damage. Generation ships, where descendants of the original crew continue the journey, face problems of social stability, genetic diversity, cultural continuity. Perhaps the only realistic option is to send not people, but machines. Autonomous probes carrying genetic material or even complete digital copies of human consciousness. They could recreate humanity upon arrival using resources of the new galaxy. But even this raises endless questions. Can consciousness be copied? Will the copy be the same person or just a simulation? How do you raise people created by machines in an alien galaxy without any cultural connection to the homeland? Will they even be human in any meaningful sense? Intergalactic travel isn't just an engineering task. It's a philosophical, ethical, existential problem for which we don't even have approximate answers. But there's another side to space, a side that makes all these discussions even more frightening. Because the universe isn't a quiet, peaceful place awaiting exploration. The universe is an arena of monstrous violence, unceasing chaos, energies so colossal that the human mind can't comprehend them. And this violence isn't somewhere far away, at a safe distance from us. It's everywhere. It's constant. It defines the very nature of the cosmos. Let's start with the most obvious: stars. We're used to thinking of stars as something permanent, stable, reliable. The sun has shone for billions of years, and it seems to us it will shine forever. But this is an illusion. Every second, the sun converts about 600 million tons of hydrogen into helium. Every second, about 4 million tons of mass disappear in the process, transforming into pure energy, according to Einstein's formula. 4 million tons per second. This is equivalent to the explosion of approximately 100 billion thermonuclear bombs every second. The sun is an unceasing thermonuclear explosion held together by its own gravity. The balance between radiation pressure outward and gravitational compression inward is the only thing preventing it from either collapsing into a point or scattering into space. And this balance isn't eternal. In approximately 5 billion years, the hydrogen in the sun's core will run out. Thermonuclear reactions will shift to a shell around the helium core. The sun will expand hundreds of times, turning into a red giant. Its outer layers will swallow the orbits of Mercury, Venus, and possibly Earth. Temperature on our planet, if it still exists, will rise to thousands of degrees. Oceans would evaporate. The atmosphere will be stripped into space. The surface will melt. Then the sun will shed its outer shells, forming a planetary nebula, a beautiful cloud of glowing gas expanding into space. At the center will remain a white dwarf, a tiny, super-dense remnant the size of Earth, but with mass of about half the sun. The white dwarf will gradually cool over trillions of years until it transforms into a black dwarf, a cold, dark ball, invisible in the darkness of space. This is the fate of our sun, relatively peaceful by cosmic standards. But for more massive stars, the end is far more dramatic. Stars with mass more than 8 solar masses end their lives in a supernova explosion. When thermonuclear fuel in their cores is exhausted, nothing can resist gravitational collapse. The core collapses in fractions of a second. Outer layers falling after it bounce off the superdense core and rush outward at enormous speed. The energy released in a supernova explosion exceeds imagination. Over several weeks, a dying star radiates more energy than the sun will radiate over its entire existence. At maximum, a supernova can shine brighter than an entire galaxy. hundreds of billions of stars. The shock wave from the supernova accelerates to tens of thousands of kilometers per second. It sweeps away everything in its path, destroying planetary systems of neighboring stars, initiating star formation in nearby gas clouds, seeding interstellar space with heavy elements: carbon, oxygen, iron, gold. All the atoms in your body except hydrogen were once created in the depths of stars and ejected into space by supernova explosions. You literally consist of stellar ash, of remains of monstrous cosmic catastrophes. But supernovas are just one mechanism of cosmic violence. There are phenomena far more extreme. Gamma-ray bursts are the most powerful explosions in the universe after the Big Bang. They occur when the core of a dying massive star collapses directly into a black hole. Part of the falling matter is ejected in the form of narrow jets moving at nearly light speed. These jets generate streams of gamma radiation of such intensity that a single gamma-ray burst at a distance of thousands of light years could sterilize Earth. A typical gamma-ray burst lasts from several seconds to several minutes. During this time, it radiates as much energy as the sun would radiate in 10 billion years. All energy is concentrated in a narrow beam, and if Earth finds itself in the path of this beam, the consequences will be catastrophic. Gamma radiation would destroy the ozone layer in a matter of seconds. Ultraviolet from the sun would begin reaching the surface unimpeded, killing all life on land and in the upper ocean layers. Simultaneously, atmospheric chemical reactions would create a dense layer of nitrogen oxides, blocking sunlight and causing global cooling. Some scientists believe that the mass extinction at the end of the Ordovician period, about 445 million years ago, could have been caused by a nearby gamma-ray burst. Then, about 85% of all marine species perished. And we can't do anything about it. Gamma-ray bursts are impossible to predict, impossible to detect in advance. Gamma rays travel at the speed of light, meaning they arrive simultaneously with any possible warning. Impossible to defend against. No shelter will save from such a level of radiation. The only thing protecting us is statistics. Gamma-ray bursts are rare enough, and space is large enough that the probability of a direct hit is low. But low probability isn't zero. Over billions of years of life's existence on Earth, it may have already survived nearby gamma-ray bursts. And whether it will survive the next one is unknown. Space is full of dangers most people never think about. Asteroids and comets capable of destroying civilization upon collision with Earth. Solar flares capable of destroying all electronic infrastructure on the planet. Nearby supernovas capable of scorching the atmosphere with radiation. And against all this violence, we dream of journeys to other galaxies. We imagine ourselves as explorers conquering the cosmic ocean. But in reality, we're fragile creatures on a tiny planet, surrounded by an environment deadly hostile to all life. Intergalactic space isn't just void, it's murderous void. Space devoid of everything necessary for life and filled with everything that destroys it. High-energy cosmic rays penetrating any protection. Hard radiation from distant catastrophes. Absolute cold approaching minus 270 degrees Celsius. Any ship embarking on an intergalactic journey would have to withstand this hostility for millions of years. Without errors, without breakdowns, without help from outside. This isn't just difficult, this is possibly impossible. And this brings us to the next question. If space is so hostile, if distances are so insurmountable, if space itself is expanding, cutting us off from the rest of the universe, what consequences does this have for any intelligent civilization? What happens to species that dream of the stars but are doomed never to reach them?
And what does this tell us about our own future? On February 23, 1987, an event occurred that forever changed our ability to understand the violence of the universe. In the Large Magellanic Cloud, a dwarf galaxy at a distance of 168,000 light-years from Earth, a star exploded. It was named SN 1987A, and this was the first supernova observable to the naked eye since 1604. But most important was something else. Several hours before light from the explosion reached Earth, neutrino detectors in Japan, the USA, and Russia recorded an unusual burst. 24 neutrinos in 13 seconds. This may seem like a negligible number, but considering that neutrinos practically don't interact with matter and pass through the planet as through empty space, 24 detected particles meant that trillions upon trillions of neutrinos passed through Earth at that moment. The energy carried away by these neutrinos constituted about 99% of all explosion energy. Visible light, X-rays, gamma rays, shockwave, everything we observe in a supernova is only 1% of released energy. The rest is carried away by ghostly particles permeating the universe unimpeded. For those 13 seconds when neutrinos passed through Earth, the energy they carried through every square centimeter of Earth's surface exceeded the energy of all nuclear arsenals on the planet. And no one noticed. Neutrinos passed through us, through the planet, through the sun, and flew further into infinity. SN 1987A allowed us to directly observe for the first time the process of stellar core collapse. We saw how a star with mass of 20 suns, in fractions of a second, transformed into an object with diameter of about 20 kilometers, a neutron star, or possibly a black hole. The density of this object exceeds the density of an atomic nucleus. A teaspoon of neutron star matter would weigh about 6 billion tons on Earth. But SN 1987A was a relatively modest event by standards of cosmic violence. There are phenomena immeasurably more destructive. Magnetars are a special class of neutron stars with monstrously powerful magnetic fields. A typical neutron star has a magnetic field approximately 1 trillion times stronger than Earth's. A magnetar is 1,000 times stronger than an ordinary neutron star. The magnetar's magnetic field is so intense that at a distance of 1,000 kilometers, it would tear a person apart into atoms. Not kill, specifically tear apart. Because the diamagnetic properties of water in our body would interact with the field, so that molecules would literally be pulled in the direction of field lines. On December 27, 2004, magnetar SGR 1806-20, located 50,000 light-years from Earth, experienced what's called a giant flare. In 1/10 of a second, it radiated more energy than the sun radiates in 250,000 years. This flare was so powerful, it ionized the upper layers of Earth's atmosphere on the night side of the planet, despite the distance of 50,000 light-years. If such a magnetar were located at a distance of 10 light-years from Earth, its flare would sterilize the planet instantly. The ozone layer would evaporate, the atmosphere would heat to thousands of degrees, oceans would begin to boil, life would disappear before it could understand what was happening. Fortunately, the nearest known magnetar is about 9,000 light-years away. But we don't know all the magnetars in the galaxy. Some may be hiding much closer, invisible to us, until they manifest themselves with a catastrophic flare. But even magnetars pale before other phenomena of cosmic violence. On August 17, 2017, gravitational wave detectors LIGO and Virgo recorded an event designated GW170817. This was the merger of two neutron stars at a distance of 130 million light-years from Earth. For the first time in history, we observed such an event not only in gravitational waves, but across all ranges of the electromagnetic spectrum.
Two neutron stars, each with mass approximately 1.5 times the Sun, but diameter of only about 20 kilometers, rotated around each other at ever-increasing speed. In the final seconds before merger, they made hundreds of revolutions per second, turning into a blurred spot in any imaginary telescope. Then they collided. The energy of this collision exceeded everything humanity has ever observed up close. Part of the matter was ejected at speeds constituting a significant fraction of light speed. Temperature in the collision zone reached hundreds of billions of degrees, thousands of times higher than in the Sun's center. It's in such cataclysms that the heaviest elements of the universe are born. Gold, platinum, uranium, all created in neutron star mergers. Every gold ring, every jewelry piece contains atoms born in monstrous cosmic catastrophes billions of years ago. In the GW 170817 merger, an amount of gold several times exceeding Earth's mass was created, simply ejected into space, scattered in all directions, to someday become part of new stars, new planets, new forms of life. Such events are called kilonovas. They occur when neutron stars, or a neutron star with a black hole, merge together. By estimates, in our galaxy, a kilonova occurs approximately once every 10,000 to 100,000 years. This is rare enough that we haven't observed a single one in the Milky Way during modern astronomy's existence. But it's frequent enough that over billions of years of Earth's history, hundreds or thousands of kilonovas have enriched the interstellar medium with heavy elements. But what happens after the merger? In the case of GW 170817, the fate of the combined object remains unknown. Perhaps it became an even more massive neutron star. Perhaps it collapsed into a black hole. Observations don't allow us to say for certain. Black holes. This very phrase carries a sense of something final, absolute, insurmountable. And this sense is fully justified. A black hole is a region of space-time where gravity is so strong that nothing can leave it. Even light, moving at the maximum possible speed in the universe, falls back. The boundary of this region is called the event horizon. Not because something happens there, but because events beyond this boundary are forever hidden from an external observer. Black holes come in different sizes. Stellar black holes form from the collapse of massive stars and have mass from several to several dozen solar masses. Their event horizon is measured in tens of kilometers. Intermediate black holes have mass of hundreds or thousands of solar masses and are still poorly studied. Supermassive black holes inhabit the centers of galaxies and reach masses of millions or even billions of solar masses. At the center of the Milky Way is a supermassive black hole called Sagittarius A star. Its mass is about 4 million solar masses. The event horizon has a diameter of approximately 24 million kilometers, less than Mercury's orbit, but gravitational influence extends thousands of light years. Stars in the vicinity of Sagittarius A star move at incredible speeds. Star S2, one of the most studied, approaches the black hole at a distance of about 120 astronomical units, approximately like Neptune from the Sun, and accelerates to speeds of more than 7,000 kilometers per second. This is almost 3% of light speed. But Sagittarius A star is relatively calm. It's barely consuming matter currently. Other supermassive black holes are far more active. Quasars are active nuclei of distant galaxies where a supermassive black hole is actively devouring surrounding matter. Matter falling onto the black hole swirls into an accretion disk, a flat structure rotating at near light speeds. Friction in the disk heats matter to hundreds of millions of degrees. The disk shines so brightly it outshines the entire galaxy. Hundreds of billions of stars. The brightest quasars radiate tens of trillions of times more energy than the Sun. They are visible from distances of billions of light years. Some quasars observed today shone when the universe was less than 1 billion years old. less than 10% of its current age. Besides radiation, quasars produce powerful jets, narrow streams of plasma ejected perpendicular to the accretion disk at speeds close to light. These jets can extend millions of light years, piercing intergalactic space and influencing the evolution of entire galaxy clusters. The energy contained in one such jet exceeds understanding. The largest known jets contain energy equivalent to complete annihilation conversion of millions of solar masses. If such a jet were pointed at the Milky Way, it could sterilize the entire galaxy. Fortunately, the nearest active quasars are hundreds of millions of light years away.
But in the past, when the universe was younger, quasars were much more common, and our own galaxy once perhaps went through an active phase. Sagittarius A star may have been a quasar billions of years ago, devouring gas clouds and ejecting jets through the galaxy's poles. Traces of this past activity may still be preserved. In 2010, the Fermi Space Telescope discovered two giant structures extending perpendicular to the Milky Way plane for tens of thousands of light years. They were named Fermi bubbles. The origin of these structures is still debated, but one hypothesis suggests they're remnants of ancient jets from Sagittarius A star. Galaxy collisions are another source of planetary-scale cosmic violence. Although individual stars in such collisions rarely collide directly, consequences are still catastrophic. When galaxies approach, gas clouds collide and compress. This causes bursts of star formation, the birth of millions of new stars over a cosmically short period. Among these stars are many massive ones that quickly evolve and explode as supernovas. Supernova frequency in merging galaxies can exceed normal by tens of times. Gas also rushes to galaxy centers, feeding supermassive black holes. Sleeping black holes awaken, turning into active nuclei or even quasars. Jets and radiation from awakened black holes pierce the galaxies, heating gas and suppressing further star formation. When Andromeda collides with the Milky Way, both these processes will likely occur. Supernova frequency will increase. Sagittarius A star and its Andromeda counterpart may activate. Over hundreds of millions of years, our galaxies will experience a turbulent period of heightened danger. But even against all this violence, there are phenomena we still don't understand. Mysteries that challenge our understanding of physics. Fast radio bursts, or FRBs, these are brief pulses of radio emission lasting milliseconds, but carrying energy the sun would radiate in months or even years. The first fast radio burst was discovered in 2007 when analyzing archival data from the Parkes Radio Telescope in Australia. Since then, hundreds of such events have been detected. Some occur once, others repeat. The source emits multiple bursts at irregular intervals. The distance to fast radio burst sources is measured in millions and billions of light years. To be visible from such distances, bursts must be incredibly powerful. But what generates them? This is one of the main open questions of modern astrophysics. Among hypotheses, magnetars with their giant flares, neutron-star collisions, neutron-star interactions with their environment, exotic objects like quark stars. Some have even suggested artificial origin, signals from extraterrestrial civilizations. But most scientists lean toward natural explanations. In 2020, a fast radio burst was detected for the first time in our own galaxy. Its source turned out to be magnetar SGR 1935 plus 2154. This confirmed that at least some fast radio bursts are generated by magnetars. But does this explain all observed bursts? We don't know. Ultra-high energy cosmic rays are another mystery. These are individual atomic nuclei, mainly protons, moving through space with energies exceeding everything we can create in Earth's accelerators. The most energetic cosmic ray was recorded on October 15, 1991 in Utah, USA. It was named the Oh My God particle. The energy of this single particle was about 300 million trillion electron volts.
This is approximately equivalent to the kinetic energy of a baseball flying at about 100 kilometers per hour. All this energy was concentrated in one subatomic proton. To accelerate a proton to such energy in the Large Hadron Collider, the most powerful accelerator on Earth, would require an accelerator the size of Mercury's orbit. What natural process is capable of this? We're not sure. Among candidates are jets from active galactic nuclei, shockwaves from gamma-ray bursts, galaxy cluster collisions. But no hypothesis explains all observations satisfactorily. Even more puzzling is that ultra-high energy particles shouldn't reach us from great distances at all. When interacting with cosmic microwave background photons, they should lose energy. This is called the GZK limit, Greisen-Zatsabin-Kuzmin limit. Particles with energy above a certain threshold can't arrive from distances more than 50 megaparsecs, approximately 160 million light-years. Yet we observe such particles. Where are they coming from? Are there sufficiently powerful sources in our cosmic neighborhood, or are we missing something in high-energy physics? Questions without answers. The universe is full of violence we don't fully understand, full of energies exceeding our imagination, full of dangers we possibly don't even suspect. And somewhere amid all this chaos is a tiny planet orbiting an ordinary star on the outskirts of an ordinary galaxy. A planet inhabited by creatures who look at the stars and dream of journeys to distant worlds. Creatures who don't understand how vulnerable they are, how accidental their existence is, how easily all this could end with a magnetar flare, a nearby supernova, a wandering black hole, an awakened quasar. We've survived so far not because the universe is kind to us. We've survived despite the universe, by pure statistical chance. Because so far, none of the countless cosmic threats has materialized in our corner of space. But on scales of billions of years, accidents accumulate. What didn't happen in 4 billion years of Earth's history could happen in the next million, or the next 1,000, or tomorrow. And this brings us back to the main question. If we're trapped in one galaxy, surrounded by hostile space, unable to reach other worlds, what does this mean for our species, for our future, for the meaning of our existence? What happens when dreams collide with insurmountable reality? There's one thought experiment that's rarely discussed publicly. It's too uncomfortable, too destructive to the usual worldview. But today, we'll go exactly there. Imagine an intelligent civilization arising 100 billion years after the Big Bang. By that time, universe expansion will have pushed all galaxies beyond the cosmological horizon. Observers of that distant era will see only their own galaxy, probably the result of several galaxies merging from their local group, floating in absolute void. Cosmic microwave background radiation, that echo of the Big Bang, will stretch to wavelengths immeasurably exceeding their galaxy's size. It will become invisible, undetectable. Light from other galaxies will disappear forever. No traces will remain that something once existed beyond their cosmic island. These beings, however intelligent they may be, will never be able to learn about the Big Bang, will never be able to discover universe expansion, will never be able to understand that once trillions of galaxies existed. For them, the universe always was and always will be a solitary galaxy in infinite darkness. Their cosmology will be fundamentally wrong, not from lack of intelligence or technology, but because the universe itself will hide its history from them. Evidence will be destroyed by time and distance. And here's what's truly frightening. How do we know we're not in the same situation? How do we know there aren't even earlier epochs? Even more grandiose stories whose traces have already disappeared by the time of our appearance. This is called the cosmological horizon of knowledge. There's a limit to what we can learn about the universe, and this limit is determined not by our capabilities, but by reality's very structure. Part of history is already lost. Part was never accessible. And part is disappearing right now while we look at the sky. Every second, approximately 20,000 stars cross the cosmological event horizon and become forever inaccessible to us. 20,000 stars per second, 1 billion stars per day, trillions of stars over a human lifetime. All these worlds, all these possibilities, all these potential stories disappear into non-existence before we can even learn of their existence. This isn't metaphorical loss. This is literal loss. Irreversible, absolute, final. And awareness of this fact generates a deep philosophical question. If most of the universe is forever inaccessible to us, if we're trapped in a tiny bubble of accessible space that becomes relatively smaller with each moment, what significance does our existence have? What meaning is there in striving for the stars if most stars are already lost? Different philosophical traditions give different answers to this question. Some say limitation makes life more valuable, not less. A diamond is valuable precisely because it's rare. If diamonds were everywhere like sand on a beach, they'd be worthless. Similarly, perhaps our existence is valuable precisely because it's limited. Because we know we can't achieve everything, because every choice has a cost in missed alternatives. Others object. They say awareness of the cosmic prison makes everything meaningless. What difference does it make what we do on our tiny planet if the universe is indifferent to us? If trillions of galaxies exist and disappear without any connection to us? If everything we ever build will be limited to a microscopic region of space? A third group offers an even more radical perspective. They say the very concept of meaning is a human invention, having no relation to reality. The universe has no meaning, it simply is. And our attempts to find meaning are no more than evolutionary adaptation, helping us survive and reproduce. The cosmic prison doesn't make life meaningless, it just shows that meaning never existed in the first place. But there's a fourth perspective. It says meaning isn't discovered, but created. That we ourselves decide what matters. If we decide our existence has meaning, it will have meaning, regardless of how many galaxies are inaccessible, regardless of how small we are on cosmic scales. Meaning isn't a property of the universe. Meaning is a property of consciousness, capable of conceiving it. Which of these perspectives is correct? Perhaps none. Perhaps all. Perhaps the question itself is posed incorrectly. But there's something all these perspectives miss. The practical aspect of our confinement. Because the cosmic prison has consequences not only for philosophy, but for our species' future. Imagine a civilization that has existed for 1 million years. This is 500 times longer than modern humanity. During this time, it mastered its entire planetary system, built orbital stations and space colonies, learned to live in space as naturally as on a planet's surface. But after 1 million years, this civilization is still limited to one star system. Interstellar travel remains impossible, or practically impossible. The star system's resources, however extensive they initially seemed, gradually deplete. The star ages, becomes unstable, planets degrade. What should such a civilization do? Accept fading, or send a desperate expedition to the nearest star, understanding the journey will take thousands or tens of thousands of years, and contact with the homeland will be lost forever? Now imagine a civilization that has existed for 1 billion years. It mastered the entire galaxy, billions of star systems, quadrillions of planets, countless beings calling themselves heirs of the original species. But after 1 billion years, this galactic civilization is still trapped. All other galaxies have long disappeared beyond the horizon. The local group has merged into one giant galaxy, and this is all there is, all that will ever be. This galaxy's stars gradually go out. New stars stop being born because gas is exhausted or dispersed. Remaining stars age, turning into white dwarfs, neutron stars, black holes. In 10 trillion years, 1,000 times longer than the universe's current age, The last red dwarfs, the longest living stars, will go out. The galaxy will become a cemetery of dead stars. Darkness, cold, void. Can intelligent life survive this? Theoretically possible. Energy can be extracted from cooling white dwarfs, from black hole accretion, from gradual matter decay. Existence can be slowed by entering states of deep hibernation between rare moments of activity. Thoughts can be stretched over billions of years, perceiving time completely differently than we perceive it now. But this will be a completely different kind of existence, not life in our understanding, rather slow fading, infinitely long agony of consciousness refusing to accept the inevitable. And eventually, even this will end. Black holes will evaporate through Hawking radiation, a process taking unimaginably long time, but inevitable. The last remnants of matter will decay. The universe will reach a state of heat death, maximum entropy, when nothing happens because there are no differences in temperature or energy, no gradients, no flows, no changes. Absolute end of everything. And then all questions about meaning will become irrelevant, not because answers will be found, but because there will be no one to ask them. This is a grim prospect.
But before plunging into despair, let's look at it from another side. We live in a unique era. Now, in the first few billion years after the Big Bang, the universe is still young. Stars still burn. Galaxies are still visible. Space is still full of light and energy. We can see the universe's past. Telescopes show us galaxies that existed billions of years ago. We can study cosmic microwave background radiation and read the history of the first moments after the Big Bang. We can understand where we came from. Future civilizations won't have this luxury. For them, the universe will be an impenetrable mystery. They'll never learn about the Big Bang, about expansion, about trillions of galaxies. They'll think their solitary galaxy is all that exists. In this sense, we're privileged observers. We live in a window when the universe still reveals its secrets, when knowledge is still possible, when questions still have answers. And perhaps there's something valuable in this, not in reaching distant galaxies, but in understanding them. Not in physical presence, but in knowledge. We can know about the universe what future intelligent beings will never be able to learn. And this knowledge itself is a form of connection with the cosmos, a form of overcoming isolation. But this consolation raises another question. If we know so much about the universe, why don't we see anyone else?
The Fermi paradox, named after physicist Enrico Fermi, who, according to legend, asked a simple question over lunch. Where is everybody? If the universe is so old and so large, if conditions for life are widespread, if intelligent civilizations arise regularly, why don't we see any signs of their existence? No radio signals, no megastructures, no traces of galactic colonization. The cosmic prison we've been talking about offers one possible explanation. Maybe civilizations exist, but they're just as trapped as we are. Maybe interstellar travel is impossible for any civilization, regardless of development level. Maybe every intelligent race is doomed to live and die within its star system, never meeting anyone else. This is sometimes called the zoo hypothesis, inverted. Not that they observe us and don't interfere, but that they can't reach us and we can't reach them. The universe is full of life, but this life is separated by insurmountable barriers of space and time. In a sense, this is a comforting hypothesis. It means we're not alone, that somewhere out there are others just like us, looking at the stars and dreaming of contact. Maybe at this very second, a being in a galaxy 1 billion light years away is asking the same question. Where is everybody? And doesn't suspect that the answer is everywhere but unreachable.
But there are other explanations of the Fermi paradox, less comforting. The Great Filter hypothesis suggests that somewhere on the path from non-living matter to galactic civilization exists a barrier that almost no one overcomes. Some stage so improbable or so dangerous that the vast majority of potential civilizations never pass it. If the filter is behind us, this is good news. It means we've already passed the hardest part. Maybe life's emergence is incredibly rare. Maybe the transition to multicellularity takes billions of years. Maybe intelligence arises only under exceptional circumstances. In any case, we're a rare exception that overcame the barrier. But if the filter is ahead of us, this is catastrophic news. It means something destroys civilizations before they become noticeable on a galactic scale. Nuclear wars, ecological catastrophes, artificial intelligence out of control, or something we don't even suspect. The cosmic prison itself may be part of the Great Filter, not because it destroys civilizations, but because it makes them invisible. A civilization trapped in one star system leaves no galactic traces. It lives, develops, reaches incredible heights and dies, unnoticed by anyone, because light from it is too faint, because distances are too great, because time is too short. Maybe the galaxy is full of ruins of dead civilizations, planets where life once thrived, but now there's silence. Artifacts buried under layers of dust and time, stories no one will ever read. And we're just another such story. Another civilization that flashed for a moment and went out, leaving no trace. But there's a third possibility. Perhaps we really are alone, not trapped together with others, but the only ones in the entire observable universe. This may seem statistically improbable. 2 trillion galaxies, sextillions of stars, countless planets. How can it be that life arose only here? But probabilities can be deceptive. We don't know how probable life's emergence is. We don't know how probable the transition from simple molecules to complex cells, from cells to multicellular organisms, from organisms to intelligence. If these probabilities are small enough, say 1 in 10 to the 100th power, then even sextillions of stars don't guarantee repetition. We may be not just rare, we may be unique. This thought simultaneously elevates and depresses. Elevates because it makes us incredibly important, the only bearers of intelligence in the universe, the only eyes through which the cosmos looks at itself, the only minds capable of asking questions and seeking answers. Depresses because it makes us incredibly lonely. There's no one. There never was. There never will be. Infinite void in all directions. And we're the only island of meaning in an ocean of meaninglessness. Which of these scenarios is true, we don't know. Perhaps we'll never know. The answer is hidden behind the same barriers that make intergalactic travel impossible. And this is perhaps the most excruciating part. Not the isolation itself, but the uncertainty. We don't know if we're alone. We don't know if there's someone out there beyond the horizon. We don't know if our existence has any significance beyond our tiny world. We're trapped, not only in space, we're trapped in ignorance. And perhaps this is the deepest prison of all. A prison of a mind capable of imagining infinity, but unable to reach it. That knows something greater exists, but can't learn what exactly. That asks questions with no answers. People love seeking hope, even in the darkest circumstances. And is there any here? Maybe. One tiny, fragile, almost imperceptible spark. We don't understand physics completely. Quantum mechanics and general relativity are incompatible at a deep level. There must be a more fundamental theory unifying them, a theory of quantum gravity, a theory of everything. And this theory could change everything. String theory, loop quantum gravity, M theory, these are all attempts to look deeper,
to understand the fundamental structure of reality at scales where space and time lose their familiar meaning. What if, hidden in these theories, are loopholes? What if there exist dimensions we don't perceive? What if the universe has back doors that allow bypassing the limitations we consider absolute? String theory suggests that our familiar 3 dimensions of space plus 1 of time are not all that exists. There may be 6, 7, or even more additional dimensions compactified, rolled up so tightly that we can't detect them directly. These dimensions exist at every point in space, but their size is so small, approximately 10 to the power of minus 35 meters, that even our most powerful accelerators can't probe them. But what if these extra dimensions can be manipulated? What if a sufficiently advanced civilization could learn to unfold them, use them for movement, create shortcuts through space-time itself? This isn't science fiction in the usual sense. This is speculation based on serious physics. Speculative, yes. Unproven, absolutely. But not impossible. Some versions of string theory allow for the existence of objects called brains, multidimensional surfaces on which our universe might reside. If our 3-dimensional space is just a brain floating in higher dimensional space, perhaps there are ways to leave this brain, move through the bulk, the higher dimensional space, and return to our brain at a completely different point. From the perspective of someone on the brain, this would look like instantaneous teleportation across enormous distances. From the perspective of someone in the bulk, this would be ordinary movement through dimensions we simply don't have access to. Is this possible? We don't know. We don't even know if extra dimensions exist. All attempts to detect them have failed so far, but the mathematics allows for their existence, and mathematics has an uncanny habit of reflecting reality. Quantum mechanics offers another potential loophole. Quantum entanglement, the phenomenon where 2 particles remain connected regardless of the distance between them, so that measuring the state of one instantly affects the state of the other. Einstein called this spooky action at a distance and didn't believe in it. But experiments have proven that entanglement is real. It exists. 2 particles separated by kilometers, or potentially by light years, remain connected in a way that defies our intuitive understanding of space. Can entanglement be used for faster-than-light communication or travel? According to current understanding, no. Although the correlation between entangled particles is instantaneous, you can't use it to transmit information. Any attempt to extract useful information from the system requires classical communication channels limited by light speed. But again, our understanding is based on current physics. What if there's something we're missing? What if quantum entanglement is a symptom of something deeper, some fundamental connectivity of the universe that could potentially be exploited? Some physicists have proposed that entanglement might be related to microscopic wormholes connecting entangled particles. If this is true, and if these quantum wormholes could somehow be enlarged or stabilized, they might provide pathways through space. This is extremely speculative. The energy requirements would likely dwarf anything we've discussed. The technical challenges would be beyond imagining. But the point is that physics hasn't closed all doors. There are still mysteries, still unknowns, still possibilities. And yet, even as we grasp at these straws of hope, we must confront an uncomfortable truth. Hope based on unknown physics is still just hope. It's not a plan. It's not a solution. It's a wish that the universe might be kinder than it appears. The responsible position, the scientific position, is to work with what we know, not with what we hope might be true. And what we know paints a picture of profound isolation. But let's approach this from another angle. Let's ask a different question. Instead of asking whether we can escape our cosmic prison, let's ask whether we need to. What if the answer to our confinement isn't expansion, but transformation? Consider what intelligence actually is. We think of it as something tied to biological substrates, neurons, brains, bodies. But consciousness might be something more fundamental. a pattern that can be implemented in different media. Already we're creating artificial neural networks that can learn, recognize patterns, make decisions. They're primitive compared to human consciousness, but they improve exponentially. In decades, not centuries, we may create artificial minds that match and exceed human capabilities. And artificial minds don't need oxygen, don't age, don't require Earth-like conditions. They can exist in the vacuum of space, can hibernate for millions of years without degradation, can be copied and distributed across vast distances. If humanity's descendants are digital rather than biological, the limitations change dramatically. Travel time becomes less relevant when you can slow your subjective experience to arbitrary degrees. Energy requirements decrease when you don't need life support for fragile biological organisms. Distance becomes less daunting when you can send copies of yourself, accepting that the original and copy will diverge into separate individuals. This is called mind uploading, or substrate-independent minds. The idea is that consciousness is fundamentally a pattern of information processing, and if you can replicate that pattern in a different substrate, silicon instead of carbon, computation instead of neurons, you preserve the essential nature of the mind. Is this possible? We don't know. The hard problem of consciousness, why and how subjective experience arises from physical processes, remains unsolved. We don't know if consciousness can be transferred, or if a digital copy would truly be the same person, or merely a simulation. But if it is possible, it transforms the equation. Digital minds could potentially endure the million-year journeys to other galaxies. They could hibernate during the voyage, experiencing the trip as instantaneous. They could arrive at their destination, construct physical bodies if desired, and continue existence in a new home. The cosmic prison remains, but its walls become more porous when the prisoners are no longer made of meat. And there's another transformation to consider. What if the future of intelligence isn't traveling through space, but transcending it? We think of the universe as this vast expanse to explore because we're physical beings confined to particular locations. But what if consciousness could exist in a form that isn't localized? What if the ultimate evolution of intelligence is into something we can barely comprehend? Distributed consciousness, beings of pure information, minds woven into the fabric of space-time itself. This enters the realm of speculation so wild it barely qualifies as science. But it's worth considering. Advanced civilizations, if they exist and survive long enough, might transform themselves in ways that make our current concerns about space travel seem quaint. Maybe they don't need to go to other galaxies. Maybe they become something for which location loses meaning. But let's pull back from these heights of speculation and return to Earth, figuratively speaking, because there's another aspect to our cosmic prison that we haven't fully confronted: the temporal aspect. We've talked about spatial limitations, how expansion and distance trap us. But there's also the question of time, not just the travel time to reach distant destinations, but the time available to us as a species, as a civilization, as a planet capable of sustaining life. Earth won't last forever. In approximately 1 billion years, the sun will have grown hot enough through its natural evolution that Earth's oceans will evaporate. The planet will become uninhabitable to life as we know it. 1 billion years sounds like an eternity, but it's only a quarter of Earth's current age. In cosmic terms, it's the blink of an eye. If humanity, or whatever we evolve into, still exists in 1 billion years, we'll need to have left Earth. Not just ventured into space, but permanently relocated to other worlds. Mars, perhaps, or the moons of Jupiter, or artificial habitats in the outer solar system, where the increased solar output will actually make conditions more amenable to life. In 5 billion years, the sun will begin its red giant phase. It will expand to perhaps 100 times its current diameter, swallowing Mercury and Venus. Earth's fate is uncertain. Some models suggest it will be consumed, Others that it will survive, but as a scorched, airless rock in a decaying orbit. Either way, Earth as a home for life will be gone. Any descendants of humanity will need to have migrated to other star systems by then, or face extinction. But here's the thing. 5 billion years is almost incomprehensibly long. All of recorded human history is less than 10,000 years.
Homo sapiens as a species has existed for perhaps 300,000 years. 5 billion years is more than 15,000 times longer than our species has existed. Will humanity, or anything recognizable as our descendants, still exist in 5 billion years? The timescales are so vast that evolution alone would transform us beyond recognition millions of times over. Most species exist for a few million years before going extinct or evolving into something else. The idea that we, or anything descended from us, might endure for billions of years is almost absurd. And yet, if we're talking about the cosmic prison, we're implicitly assuming some form of continuity, some chain of descent, biological or cultural or philosophical, connecting us to whatever distant future we're imagining. This raises a profound question about identity. If humans evolve or transform so radically that nothing of our current nature remains, if we become digital minds, or merge with machines, or disperse into clouds of nanobots, or transform into something we can't even imagine, are those beings still us in any meaningful sense? If the cosmic prison traps us, who exactly is us? Where does humanity end and something else begin? Perhaps this question matters less than we think. Perhaps what matters isn't the specific form intelligence takes, but the continuity of consciousness, of curiosity, of the desire to understand and explore. If our descendants in a billion years, whatever form they take, still look at the stars with wonder, still ask questions about their place in the universe, still strive to push boundaries and overcome limitations, perhaps that's enough to call them our heirs. But there's a darker possibility we must consider. What if there are no descendants in a billion years? What if humanity, like the vast majority of species that have ever existed, simply goes extinct? Not from some cosmic catastrophe, not from the sun's evolution, but from our own actions or inability to adapt. Climate change, nuclear war, pandemic, artificial intelligence gone wrong, ecological collapse, resource depletion. The list of potential self-inflicted dooms is long and growing. The cosmic prison becomes irrelevant if we never survive long enough to even attempt escape. If we destroy ourselves in the next century or millennium, all discussions about intergalactic travel become academic exercises, fossils of ambition from a species that couldn't manage its own planet. This is perhaps the cruelest irony. We're trapped by cosmic barriers we can't overcome, but we might not even survive to encounter them. We might be prisoners sentenced to death who spend our time debating the architecture of walls we'll never live long enough to reach. The Great Filter hypothesis suggests that something prevents most potential civilizations from reaching technological maturity. If the filter is ahead of us, it means our true enemy isn't the expanding universe or the speed of light. It's ourselves. Every day we survive as a species. Every year we avoid self-destruction. Every century we manage to keep civilization intact. These become victories more significant than any space achievement. What good is dreaming of Andromeda if we can't keep Earth habitable? What's the point of planning million-year journeys if we can't plan beyond the next election cycle? The cosmic prison reveals itself as a distraction from a more immediate confinement. Our inability to think long-term, to cooperate globally, to prioritize collective survival over individual or national interests. We're trapped not by physics, but by human nature, by tribalism, short-sightedness, greed, fear. These are barriers more formidable than any distance measured in light years, because they're self-imposed,
and yet seemingly insurmountable. If we can't overcome these, we don't deserve to escape the cosmic prison. We won't be ready. And perhaps the universe, in its wisdom, knows this. Perhaps the barriers are a test, and we're failing. But let's not end on despair. Let's consider one final perspective, one that might offer not escape, but acceptance, not solution, but peace. What if the cosmic prison isn't a prison at all, but a garden? Throughout this discussion, we've framed our isolation as confinement, as limitation, as tragedy. But limitation can also be focused. A garden is bounded by walls, yet within those walls, life flourishes. The gardener doesn't mourn the land beyond the fence. They cultivate what they have. Our local group contains dozens of galaxies, billions of stars, countless potential worlds. Even if we're forever limited to this region, it represents possibilities that would take civilizations millions of years to explore. Instead of mourning the trillions of galaxies we can't reach, perhaps we should celebrate the billions of stars we can. Instead of raging against cosmic barriers, perhaps we should explore the territory within them. The Milky Way alone contains 200 billion stars. If even a small fraction have planets, we're talking about billions of worlds, billions of potential homes, billions of unique environments, ecosystems, stories waiting to be discovered. A species that colonized just 1% of our galaxy would inhabit 2 billion star systems. That's not confinement. That's abundance beyond any meaningful measure. And remember, this assumes we remain biological and three-dimensional. If consciousness can be digitized, if minds can be uploaded, the number of beings that could exist becomes essentially limitless. Billions of individual consciousnesses could live in computational substrates the size of a planet, experiencing subjective eternities while mere seconds pass in the physical world. The cosmic prison might contain more possibility, more diversity, more richness than any unconfined species could explore in the lifetime of the universe. What we call a prison, a more enlightened species might call paradise. A bounded infinity, a garden of forking paths, a realm sufficient unto itself. This reframing doesn't deny the physical reality. Space still expands. Galaxies still recede. The speed of light remains an absolute limit. The universe still confines us. But it changes the emotional and philosophical response. From despair to acceptance. From rage to gratitude. From focusing on what we can't have to appreciating what we have. The universe gave us this island, not as punishment, but as gift. Not as cell, but as home. What we do with it, whether we cultivate it or destroy it, whether we explore it or ignore it, whether we fill it with life or leave it barren, is up to us. And perhaps that's the deepest truth the cosmic prison reveals. The boundaries aren't the point. The boundaries are just facts, neutral features of reality. What matters is how we respond to them. A prisoner rages against their cell. A monk finds enlightenment in theirs. The cell is the same. The difference is perspective. We are, all of us, bounded beings in a bounded universe. We have limited time, limited space, limited knowledge, limited power. We cannot escape our fundamental constraints. We are mortal, finite, confined. And yet within these constraints, we create meaning. We build civilizations, compose symphonies, write poetry, love each other, ask questions about the cosmos. We are prisoners who dream of infinity, finite beings who conceive of eternity, bound creatures who imagine freedom. Perhaps that's enough. Perhaps that's everything. The cosmic prison doesn't diminish us, it defines us. We are the species that looks at insurmountable walls and asks what's beyond them, that confronts infinite distance and imagines crossing it, that faces certain extinction and builds anyway, creates anyway, loves anyway. The universe will outlast us. It will expand, cool, darken. Long after our last descendant has vanished, space will continue its inexorable growth. Black holes will evaporate, protons will decay, the cosmos will reach heat death, maximum entropy, the end of all possible change. And in that infinite future darkness, there will be a moment, long past, almost infinitely improbable, barely a flicker in the vast span of time, when consciousness existed, when beings looked at stars and wondered, when life, against all odds, emerged and persisted and questioned. We are that moment. We are that flicker. We are the universe looking at itself, however briefly, however locally, however imperfectly. The cosmic prison contains us. But in containing us, it also contains something the empty void beyond cannot. Meaning, beauty, consciousness, wonder. In the end, perhaps we're not prisoners at all.
Perhaps we're the only free things in the universe, free to choose how we respond to our circumstances, free to create meaning in a cosmos that offers none, free to matter, even if only to ourselves. The bars are real, the walls are absolute, the isolation is eternal, and still we dream of the stars, still we reach for the unreachable, still we refuse to accept limitation as the final word. That defiance, that hope, that irrational, beautiful refusal to accept the verdict of physics, that is what makes us human. The cosmic prison cannot contain that. And so we return to where we began. In 100 billion years, the night sky will be absolutely black. Our distant descendants, if they exist, will see only darkness. They will never know about the trillions of galaxies that once filled the cosmos with light. But we know. Right now, in this brief window of cosmic history, we can see them. We can observe the grandeur of creation before it fades. We can measure the expansion, map the galaxies, understand the forces that will eventually isolate us completely. We are privileged witnesses to a universe that will soon hide its secrets forever. We live in the golden age of cosmology, when the evidence is still visible, when the questions can still be answered, when knowledge is still possible. That privilege comes with responsibility, to look, to learn, to understand, to appreciate what we have while we have it, to pass on the knowledge to those who come after, so that even when the galaxies have vanished beyond the horizon, some memory remains of what once was visible. We may be prisoners, but we are prisoners with a view, and what a view it is. Trillions of galaxies, each containing billions of stars, each star a potential sun for worlds we'll never see, civilizations we'll never meet, stories that will remain forever untold. The cosmic ocean surrounds our island, infinite and unreachable. We cannot cross it. We cannot even touch it. We can only look at it from our shore and wonder. But that wonder, that capacity for awe, for curiosity, for the relentless desire to understand, that is not imprisonment. That is the only freedom that matters.
And in the vast, cold, expanding universe, in this tiny corner of space and time, on this insignificant planet orbiting an ordinary star, that freedom exists. We exist. And for now, for this brief moment in cosmic history, that is enough. The prison holds us, but it cannot diminish us. We are bounded, but we are also infinite. We are trapped, but we are also free. We are alone, but we are also everything. In the cosmic prison, consciousness awakened, and in awakening transcended the very walls that confined it. Not through escape, through understanding. Not through denial, through acceptance. Not through breaking free, through being free within. The universe gave us limitations. We gave ourselves meaning.
And that exchange, that fundamental act of creation, is the only victory over oblivion that matters, the only answer to isolation that's real, the only escape from prison that's possible. Not out there, among the unreachable stars, but in here, in the space between our thoughts, in the moment between heartbeats, in the choice to care about something in a cosmos that cares about nothing. That is where freedom lives. That is where we are not prisoners. That is where, despite everything,